Okay, just to talk a little bit more about vertical asymptotes, I brought up this rational function which we talked about in the middle of the previous video. All right, we factored it and we saw that the domain was x can equal -3 and x can equal 4. Now if you look at the graph, it's pretty clear that x can equal -3 by the vertical asymptote. All right. Although I drew that blue dotted line, when you graph this, you won't see that blue dotted line, but it's you kind of add it when you're sketching it to show it's kind of like a barrier where x can equal. So like x could equal anything to the left of -3 or to the right of -3, but as you cross over that barrier, all right, x cannot equal -3. But by looking at the graph, you would never be able to tell that that x can equal 4, because if you look where x equals 4, it looks like there's a point there. All right, now if we look at this and we trace over, all right, when we get to 4, it should say undefined. All right, yep, there we go. All right, so that is a different type of discontinuity. So we have one type of discontinuity, which is a vertical asymptote, and then this type of discontinuity is a hole. All right, now why does a hole occur at 4 and not at -3? Well, the reason why is because this function is identical to y equals x minus 2 over x plus 3. So if I were to highlight this, see, you should see it in red, okay, you see that the graphs look almost identical. But with the red graph, if I were to find what point does 4, like what is y when x is 4, it would give me a value, 2.86, which would be, if I plugged in 4, it would be 2 over 7. All right. So again, these two graphs are identical because if you simplified the top equation, it would equal the bottom equation. So for every value of x I plug into the top equation, I would get the same value of y for the bottom equation, except at the point 4. All right, so the bottom equation, so the red one, is kind of like a guide which helps us find a hole. So when you're looking for a hole, a removable discontinuity, that's after you find the domain, you simplify it, and then use the simplified part to kind of use the red graph to trace over the original graph to see, well, if it's undefined at 4, what would y be if it was defined at 4? That's what a hole is. It's telling you the limit as x approaches 4 from either side. Now that's an advanced term that you'll become familiar with when you get to calculus, but a limit is just what the graph should equal, right? If we look at the black graph, all right, at 4, it's undefined, but it should equal about 2.86 or 2/7. Well, it says undefined because I highlighted the black graph, but if I do the black graph, that's what it should equal. All right, so to summarize everything I just said in one sentence, or maybe hopefully one sentence, to find a hole, simplify the rational function, and then plug in the excluded x value, and it will tell you what the value would be at the hole. When you graph it, make sure you use an open circle. Okay, so there are two types of asymptotes that you'll see when you graph, actually three, but two here that you'll see when you graph rational functions. They're vertical asymptotes, and you can see it graphically by x equals a, so that's be a vertical line, like x equals 0, pictured there in blue. And a vertical asymptote is as x approaches a specific number, y or f of x is going to approach infinity or negative infinity. And the vertical asymptote is kind of the opposite. As x gets really large, as x approaches infinity or negative infinity, y is going to approach a specific number. All right, now a graph will never cross a vertical asymptote, or at least it will never cross at a rational function. A graph of a rational function will never cross a vertical asymptote because vertical asymptotes come from domain restrictions. X can't equal those numbers. So you'll never have a point with an x value of a vertical asymptote. But that's different from a horizontal asymptote. As we'll see later, horizontal asymptotes describe the end behavior of the graph. So like what number is y approaching when x gets really large. So in the middle of a graph, towards the y-axis, all bets are off. It could cross a horizontal asymptote, it might not. You're only going to know by plugging in specific points, and you'll see as we go on when that happens and when it doesn't. But it's kind of like there's no like rule for it. There's rules for horizontal asymptotes, but to see when it crosses, you'll have to plug in extra points. Okay, so real quick, identifying asymptotes. All right, so this would have a vertical asymptote at right around there at x equals -1, another one around here at x equals 2, and another one here at like x equals 5. And it looks like the end behavior is flattening out here at around y equals -2, but notice how the graph, it kind of got covered by the asymptote, but the graph does cross a horizontal asymptote. That's what I mean by in the middle of the graph. But as x gets extreme, it's not going to really cross horizontal asymptotes. And by extreme, I mean close to infinity or negative infinity. Okay, so to find a vertical asymptote, they are the f of x will have a vertical asymptote at x equals a, where d of a is equal to 0, meaning the denominator is equal to 0, but the numerator is not. Okay? In other words, it zeros of only the denominator. Later on, we'll see that holes occur at zeros of the numerator and the denominator. But if it's just the denominator, you're going to have a vertical asymptote. If there's a 0 just to the numerator, you're going to have a 0, an x-intercept.